Ethanol and dimethyl ether are isomers, meaning they have the same chemical formula but differ in structure. Ethanol is just a liquid, but dimethyl ether is a poisonous gas. So how can we determine the difference? NMR spectroscopy is an extremely useful tool that allows scientists to determine the structure of different molecules and isomers, using concepts like nuclear spin and chemical shift. In this presentation, we will be discussing the background behind NMR, the methods of using NMR, and how NMR has actually been used in the STEM fields. A lot of the concepts that have been discussed in class are actually very useful in understanding NMR. Isomers, as previously stated, are molecules that have the same chemical formula but have different structures. Understanding the structure of different molecules is important because NMR spectroscopy is used to determine the structures of these molecules. Lewis structures are also able to give us a simple image of the structure of a molecule, like this Lewis structure of butane to the right that gives us an idea of what the molecule looks like. A good understanding of this concept will allow you to visualize the molecule when reading an NMR spectrum. Electronegativity is also important because how close a nucleus is to a very electronegative atom, like oxygen, affects its nuclear magnetic resonance. And lastly, the wave equation is also useful because the energy released during an atom's nuclear magnetic resonance is related to a frequency, which allows us to create the NMR spectrum.
In 1939, American physicist Isidore Rabi made a major improvement in beam techniques by sending a stream of hydrogen molecules through not only the inhomogeneous magnetic field required for deflection, but also through a homogeneous magnetic field, where they were subjected to radio frequency, or RF, electromagnetic energy. Energy was absorbed by the molecules at a sharply defined frequency, and the absorption caused a small but measurable deflection of the beam. This was the first observation of NMR. However, Rabi's discovery of NMR was observed under unnatural circumstances, as he used a molecular beam in a vacuum where individual nuclei were isolated from each other in their environment. In 1945, Stanford researcher Felix Bloch led an independent team that took a different approach to analyzing molecules. 1 cc of water was placed inside a glass bulb, which was wrapped around by a copper transmitter and receiver coil. These coils were optimized for a specific range of radio frequencies, which was about 8 megahertz. Bloch's team adjusted the applied magnetic field until resonance was achieved. Rather than measuring the absorption, Bloch focused on detecting a nuclear signal picked up by the receiver coil. Both Rabi and Bloch won Nobel Prize in Physics for their contributions in the development of precision methods for NMR. Since their discovery in the following decades, their methods have helped chemists closely analyze the chemical structures of many complex molecules. By the 1950s, NMR was being used on every compound for new data. In honor of Dr. Rabi's achievements in science, the International Society for Magnetic Resonance in Medicine presents the II Rabi Award each year to other scientists for contributions to NMR. Depending on the angular momentum of an atom, the nucleus of the atom will spin about an axis on a specific angle. This is known as the nuclear spin, which is a main principle of NMR. As the nucleus spins about the axis, it carries the charges, and the movement of these charges generate a magnetic field. When an external magnetic field is applied on the atom, the magnetic field from the existing nuclear spin interacts with the applied magnetic field, causing a precession of the nuclear spin, or the change in the direction of the spinning axis.
So now, how exactly does nuclear magnetic resonance work? Firstly, since its foundation revolves around nuclear spin, we can use other topics of chemistry we learned in class to understand why nuclear spin plays such a huge role. To start, an external magnetic field is applied to the system. The magnetic field created by the spinning of charge resulting from nuclear spin will interact with the external magnetic field. When this occurs, an energy transfer is possible because the interaction creates a split of nuclear energy levels. When the nucleus spins in a direction that creates a magnetic field opposite to the external magnetic field, it is at a higher energy level than when it spins and creates a magnetic field in the same direction as the external magnetic field. When the nucleus flips from the opposing direction to the same direction as the external magnetic field once radiation is added, energy is released. The energy transition corresponds to a certain radio frequency, which then reappears once again during the transition back to its original state. The reason why energy and magnetic fields are used is because the interactions allow the technique to be used. The energy is primarily used to excite the molecule, and the external magnetic field is primarily used to allow the flipping of orientation. The combination of these effects will eventually produce an energy release, which can then be converted into frequencies. By measuring the frequency, an NMR spectrum can be produced with the data to make observations and conclusions.
So let's look at how you might read one of these NMR spectra. Here we have a proton NMR spectrum, meaning that for every peak, there are corresponding hydrogen atoms in the molecule. There are three main things we can determine from an NMR spectrum. The first being chemical shift, or where the peaks lie on the x-axis. The farther left the peaks are, the closer they are to an electronegative atom, in this case, oxygen. Second is integration, or how high the peaks are. This tells us how many protons there are in the same environment. So we know from the numbers next to the peaks that they correspond with 2, 1, and 3 protons respectively. Lastly is splitting, or how many peaks there are in each area. And the amount of splitting relates to how many neighboring protons there are. We use the n+1 rule to determine the amount of neighboring protons, where n is the number of neighboring protons and n+1 is the number of peaks. Both ethanol and dimethyl ether have the same chemical formula, C2H6O. So let's look at a specific spectrum and determine whether it corresponds with ethanol or dimethyl ether. So here we have the same NMR spectrum before, and we know that it corresponds with a molecule with the formula C2H6O. But we don't know its structure yet. So let's start by looking at integration. We know that these leftmost peaks are integrated to 2, this peak is integrated to 1, and these peaks are integrated to 3. Next we can look at splitting. There are 4 peaks here, so let's use the n+1 rule, where n+1 is the number of peaks, and n is the number of neighboring protons. So there are 4 peaks here, so we know that it has 4 minus 1, or 3 neighbors. So we'll put 3n right here. There's no splitting here, which means it has no neighbors. And here it is split into 3 peaks, so it'll have 3 minus 1, or 2 neighbors. So these 2 peaks right here seem to be puzzle pieces that fit really well together, because there are 2 hydrogens here with 3 neighbors, and here there are 3 hydrogens with 2 neighbors. So we can figure out that these are probably going to be right next to each other. And because these 3 hydrogens are so far to the right, we know that they're probably not next to the oxygen, where these are so far left, we probably know that they are next to the oxygen. So we can start making our Lewis structure, where we have a CH3 group over here, right next to a CH2 group, right next to an oxygen. And then we have this lone hydrogen right here, which we can tack on at the end. So now let's check our work and make sure that these hydrogens in our Lewis structure actually correspond to the peaks. Here we have 3 protons, and here it is integrated to 3, and we know that these 3 protons have 2 neighbors right here, and it's split into 3 peaks. Here we have 2 protons, it's integrated to 2, and it has 3 neighbors, and it has 3 neighbors right here. And then here we have 1 hydrogen with 0 neighbors right here. And we can also check our chemical shift, because these 2 are the farthest left, and they're both right next to the oxygen, whereas this one is the farthest right, and it is the farthest away from the oxygen. So now we know that we have the correct Lewis structure. So now we know that we have the structure of ethanol and not that of dimethyl ether.
NMR spectroscopy has been an incredibly useful tool. By utilizing this method, people such as chemists and pharmacists, among others, are able to identify, modify, and fix compounds. For example, chemists have been using NMR to be able to synthesize chemicals more efficiently at a higher success rate as they are presented with a more precise structure of compounds. To add on, it has made it easier to interact other chemicals with compounds because scientists are able to predict and theorize outcomes. Additionally, pharmacists have been able to take advantage of this procedure to research chemical structures and to be able to produce new drugs for the industry. By having precise structures, certain structure-dependent desirable properties can be produced and added on top of the original compound. Not only that, but it also ensures the quality of products, as NMR can be used to identify impurities within compounds, creating safer and better medications. Historically, the use of NMR has been key to revolutionizing science and medicine. To summarize, Rabi and Bloch laid a foundation that would transform the world of chemistry and medicine. NMR is a powerful technique when used in the correct way. By using the principles of nuclear spin and by applying an external magnetic field, these interactions will produce a spectroscopy that can be used to determine molecular structure with precision. It is an important tool that will continue to have extreme importance both in present time and heading into the future. NMR utilizes a great composition of the lessons learned in Chemistry 1. By using topics we have learned in class such as spin quantum number, frequency, Lewis structures, intermolecular forces, and electronegativity, just to name a few, we can accurately research and develop new compounds for the future.
For most molecules, shape plays a major factor in determining the chemical properties and function. In the ethanol structure, we can see that the oxygen atom is bonded to a carbon and a hydrogen atom, with methylene groups directly by each other. In the dimethyl ether structure, the oxygen is the central atom, bonded to a carbon and another carbon on either side, and the methylene groups are separated to both sides of the oxygen atom as well. The position of the oxygen atom and the methylene groups is the difference between a harmless liquid and a poisonous gas. By using NMR spectroscopy as an analyzing tool, the differences between isomers can be determined at a precise and accurate rate.